Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 8, Lesson 4, Modeling with Quadratic Functions. After this lesson, you'll be able to use quadratic functions to model real-world situations. As we've seen in the last couple of lessons, we've had at least one example, our application problem, where it's talking about that vertical motion, throwing something up into the air and gravity pulling back down, and we can track that parabolic motion. We're going to see more of those examples today. In our model and discuss, we have something dropping from a helicopter, and we can see the height and time. So the time intervals are going up regularly, 1 second intervals, but the height, if we're looking at the change in the height, so from 350 to 335, that's a change if we're losing 15 feet. Then going into the next interval, we're losing 52 feet. The next interval, we're losing 77 feet in elevation. And then the last interval, the last second, we are dropping 110 feet in elevation. So we're falling faster and faster. Does this fit a linear model? Do we have a constant rate of change? Well, no, we don't. So linear would not be a good fit. We can see that we are increasing our distance faster and faster. So do you remember in the previous lessons where we were looking at the slope of our parabolas and the slope got steeper and steeper and steeper? Or the rate of change got faster and faster and faster? A quadratic model would better fit this situation. So what kinds of real-world situations can be modeled by quadratic functions? Let's take a look at a few. Example 1, we're modeling area. So if we are calculating area, we are multiplying two dimensions. Okay? And if we're multiplying two dimensions, then we get units squared. Okay, because we have feet times feet, which gives us feet squared, for instance. And if our units are squared, we're going to be looking at input squared. So that's how we get a quadratic function. So we have this diagram, and the length of the pool is 2x, and the width is x. And then there's this 4-foot walkway around the whole thing. So there's 4 feet on each side. There's 4 feet on each side. So really, we're taking x and we're adding 4 plus 4, which is 8. And then for the length, we're taking 2x and we're adding 4 plus 4, which is 8 for the whole length of the pool and the deck. And then if we're calculating area, remember we do length times width, and we did this when we were doing our polynomials and multiplying polynomials. So we do 2x times x and get 2x squared. And then 2x, I'll write this here so we can check. 2x times 8 is 16x, 8 times x is 8x, and 8 times 8 is 64. Combine our linear terms, and we get 24x plus 64. So there's our quadratic function for the area of the pool. So if we know the area of the pool, okay, I'll write it again, 2x squared plus 24x plus 64. That's our equation for any value of x, any feet for the width of the pool. And Carolina wants the shorter edge of the pool, or the width, to be 15. So she wants x to equal 15. So if we plug that in, we just substitute x into our equation, and we evaluate, we get 874. That would be the area of the whole pool, 874 feet squared, if she wants it to be 15 feet wide. How long will the pool be? Well, 2 times x would be 30. Suppose the length of the pool in example 1 is 3 times the width. So now it's 3x plus 8 times x plus 8. And so now let's write the equation. So we're going to distribute. I'm going to do the area model for you really quick. I have a 2 binomial, so it's a 2 by 2. I have 3x and positive 8, and I have x positive 8. I have 3x squared, 24x, 8x, and 64. Combine my like terms. To write my equation in standard form, go from upper left to lower right, 3x squared. Combine my linear terms, 24 plus 8 is 32x, plus my constant. So that would be the area of the whole pool if it's a little bit longer. So vertical motion, I mentioned this in the last 2 lessons when we were looking at throwing an object into the air. This is the equation that you will be using in physics. This represents all vertical motion due to the force of gravity. where t equals time, v naught or v sub 0, that represents initial velocity. Okay, so how fast is it going when it is released? And then h naught or h sub 0 represents the initial height. How high was the object when it was released? So this is a great formula to be familiar with, because if you know those values, if you know the initial velocity or the height, you can solve for time or maximum height, etc. So here's an example, someone jumping off a high dive. You can see we have that vertical motion, we have a maximum height, we have a total height. So the initial height is 30, so we can write this down. H naught is going to be 30. Do we know the maximum height? Well, we don't. We don't know the maximum height, but we do know the initial velocity. They tell us 16, so V naught is 16. If we plug that into our formula, then we can use that function to calculate the maximum height. So remember in the previous lesson when we had standard form, we could calculate the vertex by looking at negative b over 2a. So let's find that. Let's find the x value for our vertex equals opposite b over 2a. Let's plug in those values. X equals opposite b is 16 over 2a, which is negative 16. So negative 16 divided by negative 16 is positive 1 over 2. So our x value will be at 1 over 2. And then I'm going to evaluate, plug that into my function rule to find the y variable for my vertex. So plug in f of 1/2 into our function rule. 1/2 squared plus 16 times 1/2 plus 30. Okay, so negative 16, 1/2 squared is 1/4. So negative 16 divided by 4 is negative 4. Plus half of 16 is 8 plus 30. That's going to equal 34. So our vertex is going to be at 1/2, comma, 34. What does that mean? It means it takes 1/2 second, because t is our input, to reach a maximum height of 34 feet. Find the diver's maximum height above the water if he dives from a 20-foot platform. So now our initial height is 20, and the initial velocity is 8. So V naught is 8. So we're going to just write the formula again. H of t equals, remember it's always negative because we have a downward facing parabola. You are losing height. Negative 16t squared plus 8t plus 20. Okay, and then we're going to find our x value for the vertex. Technically, we should use t because that's our input. So our vertex is going to be t, comma, h of t, technically, since our input is represented by t instead of x. Don't be confused, it's the same formula. Opposite b over 2a. b is 8. 2 times negative 16. So t is going to be 1/2 times or divided by 2, which is 1/4. And then plug that in. So h of 1/4, I'm going to evaluate 1/4 as my input, plug that into my equation. It says negative 16 times 1/16 plus 2 plus 20. So this becomes negative 1 plus 2 plus 20. And we get our output of 21. So where's our vertex going to be? 1/4, comma, 21. So it takes 1/4 of a second to reach a maximum height of 21. Let's do another application problem. Remember, we're looking at vertical motion and represent it by a quadratic formula in standard form. Each year, the past 5 years, ticket sales for a school play have increased by $1. The director used this function to represent the relationship between the number of price increases and the average predicted revenue per show. How well does the function represent the actual revenue data? So here's our data represented in this table. And then how did we get the predicted value? So this is important. Think about what that means. Predicted value. We get the predicted revenue from using the formula. Okay, so this is from the formula, or plugging things into the equation, based off of the input, the number of price increases. And then what we have left is called the residual. Remember, it's the actual minus predicted, so it's the difference between the predicted values and the actual values, the actual y values. So this is actual minus predicted, and we have that in the table. We have the actual revenue and the predicted revenue. You will need to know how to calculate residuals on a test, so make sure you know how to do this and remind yourself actual minus predicted gives you the residual. So you can take the actual revenue minus predicted gives you the residual. Actual minus predicted gives you the residual. And sometimes the residuals are below the prediction line, the best fit line, and sometimes they're above. That's why they're positive. We can see that they're generally scattered, but does it fit the best fit line? Does this quadratic equation best fit these residuals? Are they evenly distributed? Do they form a pattern at all? Remember, if it's linear, it's going to form no pattern in the residuals. And there doesn't seem to be a pattern. I have 2 below, and I have 3 kind of far above. So let's review how to make a scatter plot on our graphing calculator. Just get out your graphing calculator, and we're going to type in the data into our stat list. So go to stat, then hit edit. And L1 is going to be our input, or our price increase, our x values. So we have 0, 1, 2, 1, 2, 3, and 4. Our y values are going to be our actual revenue. So let's plug those actual revenues in. 745, 846, 910, 952, and 1008. Okay, and when we're using our list, we're going to make sure our stat plots are on. So go to second y equals to turn our plots on. I'm going to hit plot 1 on. I do want a scatter plot. I want my list 1, my x values to come from list 1, and I want my y values to come from list 2. And we're going to hit zoom stat. That will give us a good zoomed in scatter plot. So if we look at this, it doesn't seem to be very linear. I kind of can see a curve a little bit. What if I zoomed out? What if I just did zoom standard? Can't see it. There is also a way to do a quadratic regression to see if it's a good fit. So we can go to stat again, calculate, and if we scroll down to number 5, it says quadratic regression. Our x list is coming from L1, our y list is coming from L2. Enter, enter, enter. This will give us A, B, and C for our equation in standard form for our quadratic function. And if we plug those in, it would be -8, 95.2 for our linear term, and our y-intercept, our constant, is 749.8. That's relatively close to the function that he made. This would be the best quadratic equation, so it's a pretty good fit, the one that he did. So then what if we calculated our residual plot? So let's go to stat plot again, and we're going to hit plot number 1, and instead of our y list coming from L2, we want to change that to say residuals. So we're going to go to second stat to get to our list, and number 7 is our residuals. Okay, now let's graph it. Zoom stat, and there's our residual plot. We can see those residuals. Some of them are above, and there's the 2 below, and they're pretty evenly distributed. So on this scale, since we're talking about hundreds of dollars and thousands of dollars, a residual of being off by 5 or 10, that's not that much in that scale. So we could say that these are generally pretty close to the best fit line. So this is a good fit. This quadratic model is a good fit. Even though we can come up with a better equation, a slightly better equation using our quadratic regression feature, he did a pretty good job. So let's make a scatter plot for this data table. We have this function representing the data, and let's make our residual plot. So remember, we have price increase, this is X, and this is Y, And we want to also have our predicted y values and our residuals. So I'm just going to add to the table. And we're going to have our predicted values. And then we're going to have our residuals. Let's practice doing that. So using this equation, if I plug in 0, I'm going to get 745. If I plug in 1, I'm going to have -8 plus 95 plus 745. So I would predict to get 840.8. If I plug in 2, I'd get -16 plus 190 plus 745. That would give me about, or 919. If I plug in 3, I'd have -24 and 285 plus 745. My predicted value would be 1006. And if I plug in 4, I'd get -32 and 380 plus 745. My predicted value would be 1093. So then we can calculate the residuals by doing actual minus predicted. So actual minus predicted, that's all we're going to do. Take the top column. So we have -15. We have, this is going to be positive, 9.2. This one's going to be 11. This one's going to be -55. And this one is going to be -83. So looking at our residuals, we have some above and some below. It seems like a good fit. Again, with the scale where we're looking at hundreds and thousands of dollars, being off by 15 or 50 doesn't seem to be that big of a deal, but it's mostly evenly split, so we want it to be about evenly split to make it a good representation. Example 4, the theater director at the high school wants to find the most accurate quadratic model for the ticket sales based on the data in example 3. How would the revenue be affected if the price increases one more time? So this is where we're doing the quadratic regression. I already did this on the calculator. So we plugged into the calculator our lists. L1 is our X values. L2 was our Y values, or the actual cost. Then we did stat, calc, and we did option number 5 to get to the quadratic regression. And that will give you values for A, B, and C. Make sure you have your diagnostics on, because then when you have your diagnostics on, it will give you this value for R squared. This is our correlation coefficient, which tells us if it's a good match or not. Remember, we want it to be close to +1 or close to -1. And then it will be a good match. So this is very close to +1. That tells us that it is a good equation. So these values we could plug in. -8x squared plus 95.2x plus our constant. This would be a good representation. And this is what we already saw when we practiced. So it's slightly better than the equation that he started with. So just remember, with linear regression, they give you your correlation coefficient represented as a lowercase r. Since it's quadratic and we have an x squared term, they're just representing that by capital R squared to let you know this is for quadratic regression. It's still the correlation coefficient. It's still going to tell you if it's a good fit or not, whether it's close to +1 or close to -1. So then once we have that equation, we can go in and graph that, type this into y equals, and then we can trace values and find values for different inputs. So let's get our graphing calculators again. On your graphing calculators, we'll go to y equals, and we're going to type in that equation that we got from our quadratic regression. So -8x squared plus 95.2x plus our constant 749.8. And then we can graph it. I don't think zoomstat, we're not going to be able to see it. Let's zoom out a little bit. So we can see it's a parabola. It goes up and comes back down. We should change our window, but let's see if we can calculate when x equals 5 using our graph. So just go to second trace. We'll get to calculate a value. When x equals 5, our output in our equation is going to be 1025.8. So that gives you the dollar amount when x equals 5. So that's how much it will be after the ticket price increases to $10. Try it number 4. Use the model in example 4 to determine the predicted revenue with the 6th and the 7th price increases. So now we're going to do where x equals 6 and x equals 7. Okay, we already have that in our graphing calculator, so we're just going to calculate the values for those. So going back to our graph, you're going to do second trace to get to your calculate menu. Type in the value we want when x equals 6. The value is going to be 1033. And then do the same thing, second trace to calculate the value when x equals 7. The revenue would be $1,024.20. So now the revenue is starting to decrease. It's starting to come back down in that parabola. We've reached our maximum price. So again, the price is starting to decrease. So we have reached a maximum price, a maximum revenue. And now they're losing money. They're going to start losing money. If they increase the prices too much, people aren't going to buy enough because it costs too much. So they probably want to focus on hitting that maximum value, that vertex. We made it to the concept summary for modeling with quadratic functions. You can see how they're useful if you're talking about price increases. How much do you increase before you start losing money? Or if we're looking at area, it's always going to be a quadratic function because we're doing units times units. We're going to have units squared. Remember our vertical motion equation. This is what you'll be using in physics a lot. V naught is the initial velocity, H naught is the initial height. You can calculate the maximum height if you know those two values. And don't forget to review how to calculate residuals, actual minus predicted, okay? And the actual is what's given to you in the data. If you have any questions, make sure to leave them in the comments. Like and subscribe, and come back for lesson 5.